Recording is rolling. It's Thursday, May 14th. I got theory of relativity for you guys today. And before I get to that, guys, be ready to be turning in your laptops pretty soon. We only got about a week of school left. Okay, so think about what files you need off your laptops. Go back that up to your actual personal computers. Be ready to close those down. Actually, if anybody wants to turn their laptop to me, I can check it in. Well, not during class because I want to tell you guys about theory of relativity, but in general, yeah, I have a process to check this in. Textbooks. I think everybody here how to turn out turn and check print in a textbook, but some of my other classes gotta get some textbooks. All right, so start some slides here. So we're going to start with just plain Newtonian relativity. This is going to be nothing super crazy, but well, by the end of class today, it's going to get crazy. So let's start with this boat race. Here, guys, I want you guys to solve a math problem here. You guys got calculators? Got calculators? Okay. So we're going to do this race. There's this guy in this lake versus this guy in a river. You guys see that? Lake versus river. The plan for both these guys is to paddle down 120 meters to this tree at the other end and then paddle back to the start finish line. So you guys see it's going to be a two-way race, right? Going from start finish down to the tree and then back. So 120 meters one way and then 120 meters the other way. Now the guy, they can each paddle the same speed relative to the water, 10 meters per second. Okay? But the guy in the lake, that's also his velocity relative to the land or the tree. Okay? But the guy in the river, well, he's getting a boost of 2 meters per second towards the tree, but then he's fighting the current 2 meters per second on the way back. And these guys do not tie the race. So the question is, who reaches the start finish line first? Well, the finish line? Who reaches it first? Who actually wins that race? Is it the guy in the lake or the guy in the river? Right. And if you were to set up a math equation, you would be focused on what variable to tell you who wins the race. Who finishes it in the least amount of time, right? So you guys know distance equals speed times time? Guys, could you rearrange that and get time is distance divided by speed, right? Okay, so here's headed towards the tree, and then here's headed back towards the start finish line for the guy in the boat. And it comes out to 24 seconds, right? Now, if you did a similar calculation for the guy in the river, right? Remember, he's getting a boost from the river current one way, but then he's fighting the river current back the other way. Overall, do you think this is going to take more time or less time to finish the race?
A second.
Let's see, show hands. Who do you think wins? Does the guy in the lake win or does the guy in the river win? Who thinks the guy in the lake wins the race? Guy in the lake. Who says the guy in the river wins the race? Let's see. Let's do the math. Okay, so it's the same distance, but at different speeds. The guy in the lake wins. Yeah, the guy in the lake wins because it's less time. Okay. All right, now hold on to this because we're going to need this later. All right, you guys good with that? The guy in the lake's going to win? All right. All right, now let's, all right. No, we're still sticking with just plain Newtonian relativity. Guys, when people say theory of relativity, they're not really talking about this. This is, it's like warm-up relativity. Okay? But let's say you're in the back of a truck that's moving and you're throwing a baseball and someone else over here is catching it, baseball's head, twirling them away from it. Now, you could throw the baseball at 40 meters per second. Let's have the truck going at 10 meters per second. Okay. So let's go with let's start with this guy on the left. If you throw the baseball back towards this guy, he catches it going how fast? Baseball's going left 40 meters per second relative to the truck, but the truck's going 10 meters per second right relative to the ground. So what's the velocity of the ball relative to the ground? 30 meters per second? Okay. Hang on. I pause this, grab this phone. All right, we're back. All right, so how about this guy in front of the truck? How fast? Yeah, you guys said 50 meters per second? Okay, so you guys good with that so far? Right. Again, nothing crazy. You guys could have done this back in like August or September. That's okay, right? All right, so now here's this is all going to eventually link together. What is the speed of light, or how did people originally figure this out? No, actually, you know what? There is a story go back to, I think it's the 1600s, a Danish astronomer called Ole Romer, if that's how you pronounce his name. He was watching the moons of Jupiter orbit Jupiter, and he realized that Earth was headed kind of towards Jupiter versus away from Jupiter. You're getting a little bit of a Doppler effect, and it looked like the rate that the planets were, or the moons were going around Jupiter was like speeding up, slowing down. And he got kind of a rough idea, like a kind of ballpark order of magnitude for the speed of light, okay? But it wasn't super accurate. It was off by about 30 or 40%. Okay. But 1849, this was the first time that the speed of light was accurately calculated. And here's the method, is we're going to take this cogwheel, we're going to spin it. It's got some angular velocity. And then way off in the distance, several kilometers in the background, we're going to put a mirror. All right, so I have a light source here by the observer. Here's the observer. Here's the light source on the side of the cogwheel. Right, and many kilometers in the distance is a mirror. He did this over in Paris, France. Right? And now, if the cogwheel's not spinning at all, he can see the reflection of the flame in the mirror. So he sees all that. Right? But he gives us a spin. And because it takes some time for light to travel this two-way distance, so if the mirror is like 5 kilometers back, it has to go 5 kilometers there, but also 5 kilometers back, so it's like 10 kilometer distance round trip. Right? If you get this wheel spinning fast enough, then it could be that one of these teeth covers the gap adjacent to it. You guys see that's just a tiny, tiny angle? You guys see that theta? Right? That's all it has to cover in the time that the light's going back and forth, right? But it does have to be spinning really, really fast to do this, right? Now, if you do that, you can do this. So there's distance equals speed times time. Here's the wheel spinning, and it's the number of teeth. You can do a little bit of math, and you can calculate the speed of light from. Oh, I forgot to tell you the important part. This will be going so fast that this observer can no longer see the reflection. Right? So as you speed up the spinning, the singular velocity, it looks like a door is closing on the reflection. And right when you can no longer see the reflection, you're spinning it just fast enough for all this math to work out, calculate speed of light. Okay. Back in 1849, Armand Fizeau. Okay, so we got that. So everybody's got the speed of light, right? Okay, now, next idea is okay, so you guys know how you're hearing me right now. Are the sound waves from my voice going through the air and going to your ears, and then your eardrums vibrate and the whole thing? Okay. So, because what if you took all the air out of this room? Would you even be able to hear me? No, right. Now maybe if you put your ear on the desk or on the floor, some sound vibrations can go through the floor, right? But sound needs a medium to travel through, doesn't it? Sound needs a medium, right? Guys, do all waves need a medium to travel through? Right. Well, that's the question these guys are about to tackle and answer. Right? Guys, how does light get from the sun to Earth? Is it through the vacuum of space? Okay. Now, back in the day, people knew sound needed a medium to travel through. You guys know that. Okay? And the assumption was, well, maybe all waves need a medium to travel through. And you can do different experiments with light to show it has wave properties, like a double slit experiment and get an interference pattern, right? So say, okay, well, light has wave properties. Light must be a wave, right? So what they were presuming back in the day was it must have some medium to travel through that they called a luminiferous ether. Now, if you've never heard this term, that's because this experiment I'm about to walk you guys through unintentionally disproved this idea. Okay? But what they were trying to figure out is, well, what is the relative velocity of Earth to this luminiferous ether? I mean, Earth is spinning in space. So if you're on the far side of the sun versus the close side of the sun, right, that's opposite directions. Right? The sun's revolving, or sorry, the Earth is revolving around the sun. So in spring versus autumn, right, you got opposite directions going on. Okay. I don't know if they quite knew at the time that the sun was maybe going around the Milky Way galaxy, but whether they knew that or not, they had this idea that there's probably this luminiferous ether that light is traveling on, and they want to know what's the relative velocity with Earth, right? So you guys get the premise? Okay. So here's their setup. So they have some light source here, represented by this candle flame. They have this this beam splitter, this half silver mirror, where whatever light ray hits this, 50% will pass through and 50% will bounce off at this at this 90-degree angle. So the mirror is at 45 degrees. And there's another pair of mirrors here, and then this light can route to this observation point. Now, what they were thinking was, do you guys remember that boat race from a few slides ago? That boat race, right? They say, well, the light that bounces north-south, that is not aligned to Earth's rotation or revolution around the sun. So that's kind of analogous to the guy in the lake, right? You guys remember the guy in the lake won the race? Right? But this east-west movement of the light, well, that is aligned with Earth's rotation. So one way it's going with the spin of the Earth, and one way it's going against the spin of the Earth, or the revolution of the Earth around the sun, because it's all in the same plane, I mean, pretty close. It's off by 20 degrees, or whatever. But pretty okay. Okay. So okay, that's kind of analogous to the guy in the river who lost the race, isn't it? So they were expecting that these two light rays would reach this observation point at different times. Therefore, the waves would be out of phase. And if they knew exactly how much out of phase, and they orient this at different angles at different times of the day or different times of the season, then they can figure out what is the relative velocity of Earth to this luminiferous ether, right? You guys get that premise, right? But that's not actually the result of this experiment. What they actually found was that the light waves were always in sync with each other. And it didn't matter what time of day they did this. It didn't matter what season it was. Right? They always got this result. It didn't matter how they oriented it. They could turn this whatever angle. Right? And so the conclusion is that there is no such thing as a luminiferous ether. Light can, in fact, travel through a vacuum of space. Okay? So all electromagnetic waves can travel through a vacuum. And that's actually what you guys were probably taught in a science class, right? Light can travel through a vacuum of space, right? What EM waves can, right? All right. So this has an interesting consequence, though. Let's go back to, you guys remember the guys in the truck throwing the baseball around, and you can add and subtract the velocities to get relative velocities relative to the ground, right? Well, if you take the conclusion from that Michelson-Morley experiment and you apply that to light, let's say this guy on the ground, not moving at all, so he's measuring the speed of these light beams, okay? Speed of light, and he has his cogwheel and the whole thing. So, oh, here's exactly the speed of light, right? Down to the nearest meter per second. Right? Now, let's put this guy inside the moving vehicle. Right? Just give it some velocity, whatever. Right? He's also measuring the speed of these light beams. Well, if you take the result of that Michelson-Morley experiment, guess what you get for the speed of light right here? Exactly the same number, which is weird because that's not how the baseball worked, right? The baseball you had to add or subtract the velocities, relative velocities, right? But with light, the speed of light is always the same regardless of your frame of reference, right? Regardless of frame of reference, doesn't matter how fast you're moving, right? But maybe that could kind of make some kind of sense too, because right, like right now, are you at rest or are you moving? Well, one of the first things you learn in this class is velocities are relative, right? If you're in a car going at some speed on I-95, if you're a passenger and you're blindfolded, you can't feel how fast the car's going. Right now, sitting in your desk, you can't feel how fast the Earth is spinning, right? Uh, so, like, would a microwave oven work in deep space, like at rest relative to our sun versus like on a spinning planet? Right? It all works the same. Right. Now, and there were some other experiments that are related to these that all converge to the same idea. So Einstein in 1905, he published a few papers, like these four science papers called his Miracle Year. And one of them is he tackles this idea of light having the same speed regardless of your frame of reference. He says, hang on a minute. Let's have this guy in the green hat in what's called an inertial frame of reference. So he's just sitting at rest. And we'll put this guy in the red hat inside this, Einstein-like train. So he's going with the train. Later on, you'll see a rocket. Okay. And we'll put this in motion. So maybe he starts at rest, but then eventually this goes in motion. So it's in motion. Okay? Now let's put a light source here on the floor. And let's put a mirror on the ceiling. You guys see this mirror on the ceiling? Okay. Now turn on the light and let's follow a light beam. Maybe it could bounce up off the mirror and then down, straight up and down. Okay. But guys, it's only straight up and down to someone inside the boxcar who's traveling along with it. He just sees light travel straight up and down. Isn't that right? If you're wearing the red hat, think, oh, it just goes straight up and down, right? But if you're outside the boxcar wearing the green hat, don't you actually see the light follow a different path? Doesn't it follow this diagonal? Like that it goes up this way down here, boing, right? But remember, from Michelson-Morley and some other experiments, these two guys would both perceive the same speed of light. Now, hang on a minute. How could that possibly be? Because if they both perceive the same speed of light, same speed, but they perceive different distances traveled. The guy in the red hat says, well, it didn't go very far, it just went up and down. The guy in the green hat said, no, it actually went a much further distance, travel along this diagonal path. Okay? Guys, same speed, different distances means these two guys must be perceiving different what? Times. Different times. And you can do a calculation. You can do some math here, and you can say, what is one guy's time relative to another guy's time? Okay. Guys, what shape am I tracing out right here? This is a what? A right triangle. Do you guys know any formulas to link the three legs of a right triangle? Pythagorean theorem. Aha. So I've got some distances set up. You guys know distance is speed times time. We have a special speed here. It's the speed of light. That's what c is. And c is the same for both these guys, right? But different times, right? So I got this leg squared plus this leg squared is this diagonal squared. And then you could rearrange this and solve for one guy's time in terms of the other guy's time. So this red T naught is if you are inside the boxcar, and this solid T without the subscript if you're outside the boxcar. Okay, you see it? Right. And now you can link their times. And they're related by this Lorentz factor. You guys see this whole square root? Okay. Hey guys, let's play around with this formula a little bit here. Oh, actually, you know what? I do have the full derivation for you guys. I'll just flash this up on the screen real fast. If you want to do the full proper algebra, right. Guys, there's all the algebra steps that I skipped. Okay. So anyway, that's there. Boom. Guys, let's say that here, the fastest that any human's gone relative to anybody else, probably in one of those like Saturn V rockets or something like that, right? In like a rocket that's like blasting up to the moon, right? But even that, compared to the speed of light, is very, 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 very tiny. So it's like less than 1% of the speed of light, right? So could you guys say that realistically, this any speed that anybody ever goes, even if you're on the interstate, is very close to zero compared to the speed of light? Okay. So, guys, look at that fraction where my mouse cursor is for a moment here. And if this v is very small compared to the c, this fraction right here is always very close to what? Zero? Now, what's 1 minus 0? 1. What's the square root of 1? 1. And what's t naught divided by 1? It's just t naught. Yeah, do you guys see this t and this t naught? Like, realistically, we're going to be the same, like, practically, right? So, yeah, if you jump in your car, drive up the interstate to, like, Barren Island and drive back as fast as you can, and then you compare your wristwatch time with your friends, you're not going to see a significant difference, right? So the speeds you have to go for this formula to kick in and make matter are usually called relativistic speeds. So usually like at least 10% of the speed of light, and then this starts to get more interesting, right? You know what? Here, let me play you guys a short video here. All right. Got a few videos queued up. As loud as that gets.
Once upon a time, there was a pair of identical twins, except they were not so identical. One enjoyed the settled life on Earth, while the other was more wild and adventure-seeking. One day, the wilder one decided to embark on a journey into deep space. The two embraced before parting. The rocket traveled at near the speed of light straight into the uncharted dark depths of space. It took him 5 years to realize how much he missed his twin brother. He turned around and headed straight home. Another 5 years passed before he returned at last to Earth. Upon landing, he ran to reunite with his long-separated twin brother, only to find him no longer his twin, but an old man. During his 10-year journey, 50 years have passed on Earth. He finally discovered what he truly valued more than adventures. The end.
Wait a sec.
What?
Go back. Way back to the beginning.
Okay.
Like, I thought they were the same age at the beginning. How did they end up being so different in age?
That would be an effective time dilation. Not in that way, at least. So let's imagine a train traveling really, really fast, and our explorer hops on while our settler remains behind. Now imagine that there's a light bulb fixed onto the train cart. As seen by the explorer, in order for the light to go from the light bulb and back, it only has to travel up and down.
All right.
But the case for the settler when he's looking at the train is different. In order for light to return to the light bulb, the settler sees it traveling diagonally with the train.
Oh, that's like when you're in a car and you're throwing a ball upwards. The ball returns to your hand because it only goes up and down. But to someone on the street, the ball actually has to travel with the car to return to the passenger's hand. So the ball actually travels farther than it appears to the passenger.
Yep. But there's no time dilation because the speeds of the ball are different. If the car's not moving, the ball only goes up and down. When the car is moving, however, the ball also travels forward with the car. So it is essentially thrown diagonally upwards. The forward motion added to the up and down makes it travel faster, covering the farther distance in the same time interval. Light, however, is different. No matter what frame of reference you're in, light travels at the same speed. C, the speed of light.
No duh, light travels at the speed of light.
Anyway, going back to the train, the two observers see the light tracing out different paths. The explorer sees the light travel a distance, and the settler sees the same light travel farther distance. Since light travels at the same speed, it would take longer for it to cover the distance the settler sees. So the same phenomenon to the settler would take longer time to happen than it would to the explorer, and so time on the train would appear to dilate.
But doesn't the same light argument apply to the passenger in the car? Like, if you put a light bulb in the car.
That's true. But in comparison to the speed of the car, light is so fast it is almost instantaneous. So technically, time in the car is dilated, but the change is hardly perceivable.
All right, so it says a little bit more there, but that's the main of that. All right, now think about it too. Gotta switch over here. If we got time dilations, then that can't be the end of the story, and I'll show you guys why. Okay, let's have Earth here. Okay. Let's say way off in the distance is a completely different solar system. Let's say this is, I'll say distance equals 10 light years. Okay. So if you were to shine a laser light, it would take 10 years to reach that solar system, or vice versa. If you see light coming from that solar system, doesn't it take 10 years to reach Earth? Is that right? Okay. What we're going to do is we're going to send that rocket at the speed light. Let's say at a relativistic speed towards that distant solar system that's 10 light years away. Okay. Yeah, let's say we get the rocket up to, just really simplify the numbers, like 99% of the speed of light, just something crazy. Okay. 99% of the speed of light is going or something. Okay. Now, from the point of view of someone on Earth, approximately how many years does it take to reach that solar system? 10 years. Yeah, like 10 years if you're traveling at like almost the speed of light. Okay. So that'd be the limiting factor. Okay. Because and you guys know that nothing can travel faster than the speed of light. Like there's reasons for that. It's like limit. Okay. But guys, inside the rocket, from your point of view, if you're inside the rocket, remember time dilations and all that, doesn't it take much less time? Let's say it only takes like a year from your point of view, like a year. Okay. Well, that means that this distance cannot, from your point of view inside the rocket, actually be 10 light years. Maybe it's only 1 light year because it only takes like a year from your point of view to reach your destination. So it's not just times that are dilated, isn't it also lengths and distances? That'd be true too. Right? And that's going to bring me to not only is there time dilation, there's a momentum dilation also, right? And a length contraction is how this works out. And I have some graphs for you guys. So here's relativistic time, and here's what Newton thought. Newton thought, it doesn't matter what your speed is. See this V right here? You could be going at any speed, and time beats the same for everyone. And actually, that's been our running assumption in this class for since August, right? But Einstein says, no, actually, that's not true. If you take that Lorentz contraction and divide, you get this formula. Right? It starts out being pretty close to the same, but the closer you get to the speed of light, the more vertical asymptote. Okay. And let's look at length contraction. So Newton thought, there's no such thing as length contraction. The length of everything is the same regardless of your frame of reference. Einstein says, no, actually that's not true. If you jump in that rocket, you're traveling at a relativistic speed. Your destination seems to be a lot closer than it would be otherwise. So let's do something more like this. Okay. Let's look at kind of fun. Here, do I have to go? I can't read the times there. I'm looking for 3:30. I think it's pretty close.
High, maybe. So actually, things could look very, very weird from your perspective when you're traveling close to the speed of light because all these distances get contracted. There's a famous thought experiment involving a train and a tunnel. The idea is you've got a train and you've got a tunnel which is exactly the same length as the train. And so if you're a train spotter who's standing there beside the railway watching the trains go by, you see this train approaching, and because this train's moving relative to you, you see it when it's contracted. It's a bit shorter than it should be. And that means that as it goes into the tunnel, it disappears completely in the tunnel, right? Because it's shorter than the tunnel. Like the tunnel's not moving relative to you, you're standing next to it, so therefore the tunnel is its normal length. But because this train is moving relative to you, it becomes a little bit shorter, so it disappears into the tunnel. Fine, so it actually is briefly kind of hidden at both ends of the tunnel. But now if we think about somebody sitting on the train's perspective, somebody sitting on the train, they think they're stationary, the table there in front of them, they can drink their cup of coffee. When they put it down, it just stays there. So they're in their reference frame and everything's normal. And they're seeing the countryside rushing by. And so they see this tunnel approaching them at high speed. And of course, because they're seeing this tunnel moving, the tunnel should be contracted. And so from their perspective, they should never completely disappear into the tunnel because they see a tunnel which is shorter than the train. So therefore, the train never completely disappears. By the time the back end of the train's disappeared into the tunnel, the front ends come out the other end. And that's all well and good. And okay, maybe they just agree to differ about whether the train is shorter than the tunnel or not. But unfortunately, you can then do another experiment, which is you can say, okay, so if this train spotter actually is, has a rather a lot of power, and bizarrely, someone has installed 2 large guillotines, one at either end of the tunnel, and at the moment the train disappears into the tunnel, he pulls a lever, which briefly makes these guillotines come down and then go back up again. Then from his perspective, that's fine, because the train disappeared into the tunnel. He can do that without doing any damage. Okay, from the point of view of somebody approaching the tunnel, if this happens, it's not going to be such good news because from their perspective, the train's longer than the tunnel, which means either the front of the train gets chopped off or the back of the train gets chopped off or both. Okay, and this is something that everyone has to agree on, right? Because if you actually do the experiment, either you end up with a smashed train or you don't. And ultimately, that's going to be something that everyone has to agree about. It's not something that you can just say, well, that's just a matter of perspective. That's all just relative. Like either the train gets broken or it doesn't.
So what happens?
So there is a resolution to this paradox, and the resolution to this paradox turns out to be something very fundamental in relativity, and it's called the relativity of simultaneity, which basically means which things which are simultaneous in one reference frame are not necessarily simultaneous in another reference frame. So in fact, both of these people agree that the train doesn't get smashed, but the reason why they agree the train doesn't get smashed is different, right? The guy who's pulling the lever says, well, the train obviously didn't get smashed because it was shorter than the tunnel, so that was fine. The guy in the train sees something completely different in that what he says is that actually what happened is the train was approaching. Before it went right through the tunnel, the front guillotine came down and went back up again. Then after it had pretty much passed through, the back guillotine came down and back up again. And so actually they kind of missed the train as it went through. And so this is what both of them see. They both agree that actually the train's fine. But the reason is that because the things which were simultaneous in one reference frame, the guy who was just standing next to the tunnel said these things happen both at the same time. The guy who's in the train said actually no, one happened first, then the other. And so that's the resolution to the paradox, is that this whole concept of simultaneity kind of goes away in special relativity. That things which one person says both these things happened at the same time, somebody else will say no, actually that one happened first and that one happened second. Because whether things happen at the same time really depends on what reference frame you're measuring them in.
But what's the fact? Did the train disappear in the tunnel, or did it fall out the ends? What actually happened?
Both. It just depends on whose reference frame you're in, right? In one reference frame, that's exactly what happens. If you think about it, the train sticking out of both ends of the tunnel relies on somebody's simultaneous measurements, right? The front was sticking out at the same time that the back was sticking out. And because different people disagree about simultaneity, it's quite possible for them to disagree about whether both ends of the train are sticking out of the tunnel at the same time.
How does this go down when you teach this to students?
The students love it, I have to say. I mean, one of the really nice things is, although we avoid all the maths in these videos, actually the maths you need to do this properly isn't very hard. The most difficult maths you need to do this properly is trigonometry and just basically Pythagoras' theorem.
Yeah, there you go. All right. Sorry, guys, my computer's being weird here. All right, back here. So, got this graph. I guess from momentum is mass times velocity, but then Einstein says, well, it starts off that way, but a little more complicated. Right? All right. Ooh, if you ever see I have a kind of a fancy version of this Minkowski space-time diagram. Sometimes you'll see a simpler one that just has an x-axis to represent space and then a vertical axis to represent time. Now I'm throwing in another dimension here. Can you guys think it's sort of 3 dimensions? Okay, but this whole xy plane now actually represents 3-dimensional space. Okay, right. So this xy plane is actually a 3-dimensional space, and this vertical axis running straight up, represents time. Now, if you take time multiplied by speed, in this case the speed of light, that could also be like a distance dimension, which allows you to create this 45-degree angle. Okay, now 45 degrees. Okay, what does that mean here? Let's say right now we are sitting at this origin point, the 0, 0, 0. You see that? Okay. Now time is ticking forward, but all of us right now are just sitting at rest. So you can think of it as we're just like moving up this axis as time ticks forward, but we're not actually changing location. Right? I'm ignoring the Earth spinning around the sun and that whole thing, right? Okay. So we're not moving, but time's ticking forward. Right? But if you do move, guys, if you do move through space, then don't you deviate from this line and maybe you move like, see my mouse cursor moving off at some angle, right? But you're limited by how fast you can go. Guys, isn't it true the faster you go, the more extreme this angle would be? And if you go at the speed of light, you hit this 45-degree angle. So all photons are traveling right along this diagonal, this 45-degree diagonal, right? Which also means that anything that could affect you up to this point, from the past, is somewhere in this green cone labeled past. And anything that you can affect going into the future in space and time is in this future cone. Okay? Right, so if you were to try to, let's say we had some astronauts on the moon and you wanted to send a message to them in like 1 second. Well, that could never happen because at light speed, you can't send a signal to the moon in 1 second. It's just too far away. Okay? So that would lie outside here, like outside this cone. So you cannot affect anything on the moon in that short interval of time. Okay? Well, you know what else I meant to mention? Let me go back some slides. Okay. You guys know that photons are traveling at the speed of light. Anything that has no mass is traveling at the speed of light. Right? What does the universe look like from the point of view of traveling at something at the speed of light? Like if you actually hit this asymptote, would you see all of time happening all happening at once? Wouldn't you? Yeah, there'd be no such thing as time. And then from this length contraction point of view, if you reach the speed of light, wouldn't the entire universe contract to like a 0 point?
Yeah.
So from the point of view of photons, you can make the case that there is no such thing as space and time. Maybe you only perceive space and time because you have mass. Right? Yeah. Interesting thought too, right? Yeah. All right. Let's see. Okay. Ooh. You guys seen this one? E equals mc squared. Now there's a whole proof that leads up to this. I'm just showing the last couple steps. Because this is mass energy equivalence. This is the energy of nuclear reactions. So do you guys remember that whole class chemistry you took where did you guys learn about conservation of mass? Right. So you guys ran some chemical reactions, and if you add up all the mass of the products and all the mass of the reactants, doesn't it always equate? Mass is always conserved. Right. Now that's not true for a nuclear reaction. If you run some, say, uranium-235, your nuclear reaction, it looks like there's missing mass. But that difference in mass, if you multiply by the speed of light squared, will tell you exactly how much energy you're getting from that nuclear power plant. Do like that. Two kinds of nuclear reactions. There's fission and fusion. Now, if you ask, like, what's the mass of a nucleon? You guys see a nucleon here? Guys, what is a nucleon? It could be a what or a what? Proton or a neutron? Okay. So there's another version of this graph that looks like the upside down version of this, where it's in terms of mass of a nucleon. This is in terms of binding energy. Okay. But it actually depends on what atom you're in. So if you're in a hydrogen atom versus helium versus iron versus uranium, right? These are all different values. Right? And okay, where this all changes over is at iron. Right? So that Fe could be iron right there. Right? So if you take a uranium atom and you split it into smaller atoms, and here's one of the more common reactions you can have. So U-235, you can bombard with a neutron, and that'll split into krypton and barium and 3 neutrons and a bunch of energy, right? But it really has to do with the height change from uranium to some of these smaller atoms, right? Which is kind of small change right here. Okay? But you guys see to go from hydrogen to helium, that's a much, much, much bigger change. It's like hundreds of times bigger, like almost 1,000 times bigger. So if you can get these isotopes of hydrogen and get those to fuse together, right? This is the energy that say you get from the sun, right? So the sun or like any stars are going through this fusion process. Right? Now this is the one we haven't quite figured out how to turn into a power plant to get energy on the grid, but yeah, hopefully a near future technology. Right? All right, let's switch over to. Let's see, am I ready for general relativity? Yeah, let's do some general relativity here. General relativity. Okay. All right. So, guys, question for you guys. If you were in, guys, do you guys have cell phones with you? Cell phones? Do those cell phones have accelerometers in them? So if you start waving around and it kind of knows the orientation, if you turn it, right? So your cell phone can detect motion because there's an accelerometer in there. Okay. Now, guys, what if you were to go into deep space? You're just floating around. Could you guys imagine there's an astronaut floating around in deep space? Right. Guys, critical thinking question. What does your accelerometer read in deep space? Zero? Yeah, would that be right? Zero? Right? Because you're just floating around? Okay. Well, if that's true, then sitting in your desk right now, what does your accelerometer read? Gravity field. Yeah, it reads 1G. Guys, your cell phone thinks that you are accelerating at 1G. And guess which direction? Up. 1G up. Let's go back to this thought experiment from Einstein back in the day. He was thinking about this guy falling off a building and realized that from the point of view of that person, it would be pretty impossible to tell the difference between that or being in deep space just floating around, right? You can make the case for like tidal forces or something, but otherwise it'd be an identical experience and you can't tell the difference, right? Or, guys, you just sitting in your desk right now, how do you know that you're not in a rocket in deep space accelerating upward at 9.8 meters per second squared? Yeah. Welcome to the Matrix. Because, guys, if it's a closed room, Again, identical experience, it'd be impossible to tell the difference. Maybe unless you like rigged up a Foucault pendulum or something. Okay, but besides that, because these are identical experiences, and your phone accelerometer would agree to that. So what I'm trying to get at here is that here, let me bring in another situation. Is what if you're sitting in a car, you're a passenger in a car, and the car accelerates forward? Do you feel that?
Yeah.
You can feel that, right? Because the backseat of the is pushing against you and causing you to accelerate because there's a force there, right? So what this is all leading up to is Einstein's making the case here that gravity is not actually a force. So this whole thing about like, oh, there's this inverse square distance attraction between the Earth and the Moon, or between you and the Earth, whatever, right? From a Newtonian point of view, Einstein says, well, actually, that's not exactly true. Right? And Einstein's general relativity says that NASA works this fabric in space time, and that say like the Moon orbiting the Earth, what the Moon is actually doing is it's following a straight line in curved space time. So the Moon is only traveling ever in a straight line according to the law of inertia. But because the space time is curved around the Earth, from the point of view of Earth, it looks like it's orbiting the Earth. Okay? What else do I want to say? I forget, something like that. Right. Anyway, there's general relativity. Right. Yeah. Right. This was actually able to explain some phenomenon that cannot be explained by Newtonian physics. I'm gonna dig through my PowerPoint real fast and see if I can find one of these. Yeah, it's this photograph. No, here. Sorry, it's gonna be weird. I'll show you here. Okay, guys, it's this photograph right here. This is one of the points of evidence. There are some other ones too. Like if you look at the orbit of the planet Mercury, it doesn't follow exactly what Kepler and Newton said it should. Right, but in 1919. There's this eclipse photo taken. Now, why is the eclipse important? Because, guys, what's by far the largest mass on our solar system? Yeah, the sun. It's like more than 99% of the mass. It's massive enough to be able to bend the light around it. But during the day, can you see the stars around the periphery of the sun?
Yeah.
No, because it's too bright. But you would be able to see them if the moon was exactly blocking out the sun. Now, since the sun has 400 times the diameter of the moon, but it's also 400 times further away, the moon can just barely exactly cover up the sun. Okay? And then if you look at the positions of the stars right around in this photograph, they are not exactly where they would be if the sun was, if you just had like a regular night sky. They're actually shifted a little bit, but they're shifted exactly as much as Einstein predicted according to his theory of relativity.
Because of it, golfers choose better clubs. Skiers find faster ways down mountains. The uses for this innovative tool are virtually unlimited. It's called the Global Positioning System, better known as GPS.
So exactly how does this incredible tool work? So imagine you're on a field and you wanted to triangulate where you were because you know the positions of things in the distance that you can see. By measuring the direction to one object and another object, you can figure out where you would have to be in the field. Well, GPS is like that, but it's larger. It's in all three dimensions, not only where in the field, but how high. And also it's measuring time. You have 4 satellites. They're sending you signals. And you're measuring accurately where the satellite appears to be and when the signals are sent. And from that, you can figure out where you are on the Earth's surface.
Global Positioning System is a network of over 30 satellites orbiting 20,000 kilometers above us. They move at a speed of 14,000 kilometers per hour. Each satellite follows one of 6 orbits arranged so at least 4 satellites are visible from any point on Earth. The satellites constantly transmit signals, easily picked up by anyone with a GPS receiver. Each signal contains information on where the satellite is and what time the signal was sent. Using this information, the receiver calculates its distance from the satellite. This is done by multiplying the signal speed, the speed of light, by the time the signal traveled. The receiver then repeats this procedure for 3 more satellites. narrowing down its location to within a few meters. To achieve this incredible accuracy, the timing information from the satellites must be extremely precise. So inside each GPS satellite is an atomic clock, the most accurate timing device ever created. The GPS is so precise, it must take into account a number of subtle effects. Some of these are predicted by Einstein's theory of relativity, an idea that revolutionized our understanding of the universe. This theory includes special relativity and general relativity. Special relativity is a theory of space, time, and motion. Key to it is the fact that motion alters time. We see time running slower for a clock that's moving relative to us. Satellite-based GPS clocks are moving past us at 14,000 kilometers per hour. Because of special relativity, they gradually fall behind clocks in Earth-based receivers at a rate of 7 microseconds per day.
After Einstein formulated the theory of special relativity, he went further ahead and he proposed his theory of general relativity, which is not only a theory of space-time, but it's a gravitational theory.
Key to Einstein's theory of general relativity is the fact that gravity alters time. Clocks farther away from Earth, where gravity is weaker, run faster than clocks closer to Earth, where gravity is stronger. The GPS satellites are located 20,000 kilometers above Earth, where gravity is much weaker than on the surface. Due to general relativity, satellite clocks run 45 microseconds faster daily. When we combine the effects of special and general relativity, satellite clocks run 38 microseconds faster every day. This may not seem like much, but if uncorrected, all GPS measurements would be off by 11 kilometers daily.
The effects of relativity on
As a particle physicist, I study the elementary particles and how they interact on the most fundamental level. For most of my research career, I've been using accelerators such as the electron accelerator at Stanford University just up the road to study things on the smallest scale. But more recently, I've been turning my attention to the universe on the largest scale. Because as I'll explain to you, the questions on the smallest and the largest scale are actually very connected. Okay? So I'm going to tell you about our 21st century view of the universe, what it's made of, and what the big questions in the physical sciences are, or at least some of the big questions. So recently, we have realized that the ordinary matter in the universe, and by ordinary matter, I mean you, okay? Me, the planet, the stars, the galaxies, the ordinary matter makes up only a few percent of the content of the universe. Almost a quarter, or approximately a quarter, of the matter in the universe is stuff that's invisible. By invisible, I mean it doesn't absorb in the electromagnetic spectrum, it doesn't emit in the electromagnetic spectrum, it doesn't reflect, it doesn't interact with the electromagnetic spectrum, which is what we use to detect things. It doesn't interact at all. So how do we know it's there? We know it's there by its gravitational effects. In fact, this dark matter dominates the gravitational effects in the universe on a large scale. And I'll be telling you about the evidence for that. What about the rest of the pie? The rest of the pie is a very mysterious substance called dark energy. More about that later, okay? So for now, let's turn to the evidence for dark matter. In these galaxies, especially in a spiral galaxy like this, most of the mass of the stars is concentrated in the middle of the galaxy. This huge mass of all these stars keeps stars in circular orbits in the galaxy. So we have these stars going around in circles like this. As you can imagine, even if you know physics, this should be intuitive, okay? That stars that are closer to the mass in the middle will be rotating at a higher speed than those that are further out here, okay? So what you would expect is that if you measured the orbital speed of the stars, that they should be slower on the edges than on the inside. In other words, if we measured speed as a function of distance, this is the only time I'm going to show a graph, okay? We would expect that it goes down as the distance increases from the center of the galaxy. When those measurements are made, instead what we find is that the speed is basically constant as a function of distance. If it's constant, that means that the stars out here are feeling the gravitational effects of matter that we do not see. In fact, this galaxy and every other galaxy appears to be embedded in a cloud of this invisible dark matter. And this cloud of matter is much more spherical than the galaxy themselves. And it extends over a much wider range than the galaxy. So we see the galaxy and fixate on that, but it's actually a cloud of dark matter that's dominating the structure and the dynamics of this galaxy. Galaxies themselves are not strewn randomly in space. They tend to cluster. And this is an example of a very actually famous cluster, the Coma cluster. And there are thousands of galaxies in this cluster. They're the white, fuzzy elliptical things here. So these galaxy clusters, we take a snapshot now, we take a snapshot in a decade, it'll look identical. But these galaxies are actually moving at extremely high speeds. They're moving around in this gravitational potential well of this cluster. Okay, so all these galaxies are moving. We can measure the speeds of these galaxies, their orbital velocities, and figure out how much mass is in this cluster. And again, what we find is that there is much more mass there than can be accounted for by the galaxies that we see, or if we look in other parts of the electromagnetic spectrum, we see that there's a lot of gas in this cluster as well. But that cannot account for the mass either. In fact, there appears to be about 10 times as much mass here in the form of this invisible or dark matter as there is in the ordinary matter. Okay? It would be nice if we could see this dark matter a little bit more directly. I'm just putting this big blue blob on there, okay, to try to remind you that it's there. Can we see it more visually? Yes, we can. And so let me lead you through how we can do this. So here is an observer. It could be an eye, it could be a telescope. And suppose there's a galaxy out here in the universe. How do we see that galaxy? A ray of light leaves the galaxy and travels through the universe for perhaps billions of years before it enters the telescope or your eye. Now, how do we deduce where the galaxy is? Well, we deduce it by the direction that the ray is traveling as it enters our eye, right? We say the ray of light came this way, the galaxy must be there. Okay. Now, suppose I put in the middle a cluster of galaxies, and don't forget the dark matter. Okay. Now, if we consider a different ray of light, one going off like this, we now need to take into account what Einstein predicted when he developed general relativity. And that was that the gravitational field due to mass will deflect not only the trajectory of particles, but will deflect light itself. So this light ray will not continue in a straight line, but will rather bend and could end up going into.
You guys have a good day.
Where will this